Hello everyone and welcome to this new amazing chapter, which is complexity analysis. What we will learn together in this lesson is, first of all, what is time complexity and what is the big O notation. Then we will analyze the time complexity of some example algorithms, and then we will dive into the space complexity and also analyze the space complexity of some example algorithms. So let's start. What is time complexity? By definition, time complexity is the way of measuring how much time your algorithm takes to execute, the so-called runtime, according to the input size. As you know, in computer science and technology, performance is a super important aspect that should not be neglected. Thus, we need a universal way of comparing the performance of two algorithms in order to figure out which one is better and in what scenarios. Well, why not just run both of them on the same input and compare the time it takes both to complete? For example, if when some input is given, the first algorithm takes 1.23 seconds to execute and the second one takes 5 seconds, we might say that, okay, that's it, the first algorithm definitely wins. But that's not true. And that is because the time it takes an algorithm to execute depends on too many factors. Besides that algorithm's performance, one of them, and probably the most important one, is the input size. What should we do if on a larger input, the first algorithm now takes 7.7 seconds to execute, and the second one now executes in 6.5 seconds? Should we change our minds and declare the second algorithm the best? Well, we don't know. Because as I've said, this 6.5 seconds depends on too many factors. The algorithm, the resources of the computer that you run that algorithm on, the language in which the algorithm is written, and even what other background processes your computer is busy with. Also, if you think about it, this process of comparing two algorithms is very unproductive. After coming up with the algorithms, you have to write them, you have to execute them, and then you compare those runtimes. So imagine how many lines of code were written in vain just to find out later that that algorithm is not even close to the best one. So what is the solution to this? The solution is finding a theoretical way of expressing the runtime according only to the input size and before the algorithm is even written. And this is what we call the Big O analysis of the time complexity. I will repeat this because it's super important. The time complexity should be expressed only according to the input size. And let's imagine a fictional dialogue between me and Mircea. Hey, I've tested and my algorithm takes 1 second to execute. Cool, what was the input size? 10 numbers? You know that this algorithm is supposed to do well with 1 million numbers, right? Oops. Now what we should do is find the time complexity of it. So we don't express the time complexity or the performance of an algorithm in seconds because they are strictly related to the input size. The larger the input size, of course, the larger the time it takes that algorithm to execute. Okay, I think that's enough theory for now. Let's have our first time complexity analysis of an algorithm. Let's suppose we are given a positive integer n and we should output the sum of the numbers 1, 2, 3, n. Now, someone who missed his math classes might come up with an algorithm like this. Have a variable to compute the sum, initially equal to 0, then iterate through each number from 1 to n, add that number to the sum, and in the end return the sum. As simple as that. Now what is the time complexity of this algorithm? Now it's time for the simplest and most important thing that you should know about time complexity. Time complexity depends strictly on the number of fundamental operations that some algorithm does. That's it. All we have to do is count how many fundamental operations are performed in total by the algorithm until it finishes execution. The fundamental operations are the ones that we consider that it doesn't take a significant amount of time to perform. And some of them are addition, subtraction, product, division, assigning, bitwise operations, the return statement inside functions, and comparisons. Bear in mind that the data type that we work with is super important. For example, if x and y are integers or floats, this is considered a fundamental operation. But if they were strings, then we don't perform any more addition but concatenation of strings, which is not a fundamental operation and takes more time to execute. But for start, we will work only with integers, so don't worry about that. Let's see what are the fundamental operations that we perform in this algorithm. The first one is assigning the value 0 to the variable sum. The second one is adding the value I to sum. And the third one is returning the sum. The first operation happens only once. The last one also once. But the second one, which is performed inside a for loop that performs n iterations, is going to be performed n times. So our algorithm performs n plus 2 fundamental operations. This is not the time complexity. The time complexity is expressed using the big O notation. You don't have to know any mathematical property of this function, as we will discover them by practicing on algorithms and you will see how intuitive they are. All we need to do here is wrap n plus 2 inside the big O notation. And remember, the time complexity was a theoretical way of expressing the runtime according only to the input size. So the first property that you should know about the big O notation is that we don't take constants into account. So in this expression n plus 2, it is pretty clear that the most important factor is n, and as n becomes larger and larger, the runtime will become greater. But 2 is just a constant which is irrelevant. So we remove it and we say that the final time complexity is big O of n. Now, someone who didn't skip his math classes would come up with a second algorithm that will just return the Gauss sum, which is n crossed n plus 1 divided by 2. What are the fundamental operations here? We have the product, we have the addition, we have the division, and then we have returning the result, for a total of 4 fundamental operations. As you can see, this number 4 doesn't depend on n. In this case, where the number of fundamental operations is constant and it doesn't depend on the input size, we say that the time complexity is constant. And using the big O notation, we note this as big O of 1. Which one of these two do you think is better? The first one, which had big O of n, or the second one, which has big O of 1? Of course, it is the second one. It might be no visible difference for n equals 10 or n equals 20, but when n equals 1 million, the second one definitely executes faster. Now it's time for analyzing some example algorithms. We start with the first one, which has a loop inside it. In case of loops, we always need to ask how many iterations does this loop make? And the answer here is n. Then we need to ask another question. How many operations are performed inside the loop, which is only 1. And this is why the time complexity of this algorithm is big O of n. Then we had the second example, which performs a constant number of operations, so we say that the time complexity is big O of 1. Now for the next example, let's have an algorithm which has 2 nested loops inside it. Let's say that in the input we are given a positive integer n and an array A of n elements. And we need to sort this array. We can use a classic algorithm for this, which is selection sort, that operates by choosing each index I between 0 and n-2 and making sure that we put the right value on index I. For that, we use another variable min index, which should store the index of the minimum value from the subarray starting at position I plus 1 and ending at position n-1. So we have another for loop that updates this min index if we find the value less than the current minimum. And when the loop terminates and we know the index of this minimum value, we swap the current value on position I with that value at the minimum index. When this algorithm terminates, the array A will be sorted. You can take a couple of moments in order to understand better how this algorithm works. After this, let's see what are the fundamental operations performed here. We have these 2 assigning operations, min index equals I and min index equals j. Then we have the comparison inside the if statement. Then we have the swap functions, which actually performs 3 assignment operations inside it. Now, in order to count the total number of operations performed, we need to take the loops into account. and we always start from the inner ones. As you can see, for each value of j, we perform 2 operations. So how many iterations does this inner for loop do? N minus I minus 1. Now, for each value of I, we perform 1 assignment operation, 2 crossed n minus I minus 1 operations from the for loop, and 3 operations from the swap function. As you can see, the number of operations performed inside the for loop depends on the value of I. So in order to count the number of total operations, we need to take each value of I and add the number of operations performed on that iteration to the answer. For I equals 0, there are 2 crossed n plus 1 operations. For I equals 1, there are 2 crossed n. For I equals 2, 2 crossed n minus 1. And so on and so forth. For I equals n minus 2, there are 2 crossed 3 operations. If we add this together, we get a total of 2 crossed 3 plus 4 plus ... plus n plus 1, which we can also write as 2 crossed 1 plus 2 plus 3 plus ... plus n plus 1 minus 3, and we can apply the Gauss sum, so we will get 2 crossed n plus 1 crossed n plus 2 divided by 2 minus 3, which is n plus 1 crossed n plus 2 minus 6. This can be written as n squared plus 3 crossed n minus 4. And now this is very important. When having polynomials in time complexities, we should always pick the factor that is the most significant. As n grows in value, the factor that most significantly increases the total number of operations is n squared, not 3 crossed n and not minus 4. We pick this factor, and this is exactly where we say that the time complexity is big O of n squared, which is of course worse than big O of 1 or big O of n. Now let's take another example, an algorithm which has sequential statements. Let's say that the input is again a positive integer n and an array A of n elements, and as the output, we should return true if A consists only of unique elements and false otherwise. We might come up with an algorithm that first sorts the array, of course using the selection sort, and then we can traverse the array to check if 2 consecutive elements are equal. What are the fundamental operations here? The comparison inside the if statement and the returns. The for loop makes at most n-1 iterations, and each of the returns is performed at most once. So even in the worst case scenario in which the for loop performs all the n-1 iterations, and then something is returned, we will have n operations and the time complexity of big O of n. The first step of sorting the array using selection sort is executed in big O of n squared. So is the time complexity big O of n squared plus n? No. Just as in the previous example, when we have polynomials inside time complexities, we always pick the factor that is the most significant, which is n squared, so the time complexity is big O of n squared. So remember, when you have sequential statements, you might add the time complexities of all the steps, but in the end, you should only keep the most significant factors from that final time complexity. For the next example, let's use an algorithm that has if-else statements. Let's suppose that if n is even, we call a function do something even with the argument n, and otherwise we call a function do something odd with the argument n. And let's suppose that the time complexities of these functions are big O of n and big O of n squared respectively. A lot of algorithms behave differently depending on the input, but what you should remember is that the time complexity is always analyzed in the worst case scenarios. Here, the worst case scenario is of course when n is odd, so we say that the time complexity of this algorithm is big O of n squared. And this was the first lesson of the chapter Complexity Analysis, where we discussed the following main ideas: time complexity, big O notation, and then we have analyzed some example algorithms. Thanks a lot for your time, and I can't wait to see you on the next lessons, in which we will do some time complexity analysis practice, and then we will learn about space complexity.